Okay, so I wanted to share with you a cool trick that I came across that helps save money in the labeling stage using clustering, as the name suggests. This is the problem we are facing. We have a law firm that has a lot of contracts, but they're not labeled. And what the law firm wants to achieve is to be able to classify all of those documents into one of three clusters, A, B, or C, one of three classes, A, B, or C. Now, labeling a contract is not cheap because lawyers aren't cheap. And a lawyer needs to read a contract in order to label it. On the upside, contracts are very similar to one another. So lawyers love the copy-paste, but between us. So let's try and take advantage of this fact. This is the idea. First, we try to cluster contracts together. Then we try to take one example from each cluster and let our expensive lawyer label it, and then saving money. So the first stage we need to take is to take a document, a contract, and convert it in some magical way into a vector. Now, there are a lot of ways to do this. The most simple one is just to count how many words are in each document, and then you have this large vector, the size of the vocabulary. Other more sophisticated ways, for example, TF-IDF, also account for the frequency of words. Maybe words like the, of, and aren't as informative as other words. Other methods there are a lot of neural networks method. I don't want to elaborate more on this. Just you need to have a method to take your contract, take your document, and convert it into a vector. This is a three-liner in sklearn that does TF-IDF for you. If you only want the counts, then use the first two lines. Very easy, very straightforward. Next, we want to cluster all of those vectors that we built together. Now, usually when people think about clustering, they think about k-means. K-means is a top-down approach, meaning that you assign k clusters, k centroids, and then you shake them and move them around in some magical way, and at the end you get a division of the space into k clusters. The other approach is called bottom-up. You start with n clusters, n being the number of documents, and then you start to merge them together according to distance, one by one. At the end of this process, you need to decide when to stop, what is the minimal distance that is still important. And you get a variant number of clusters. This is how you do hierarchical clustering in Python. Pretty simple. SciPy has a very easy implementation for it. Hierarchical clustering has three hyperparameters. The first is what distance do you use? There are a lot of choices in SciPy. Next is what is the minimal distance that you need to account for, the minimal distance that you still consider things to be in the same cluster. This is called the cutoff distance. And the last hyperparameter is where do you measure the distance from? Do you measure it from the center of the cluster? Do you measure it from the bound, from the furthest point? Once we decided on an embedding method and a clustering algorithm, we have clustering, and now we want to evaluate it. So there are a lot of ways to evaluate clustering algorithms in the general sense. But in this context, we want to find the best cluster that would help us label the data. So a neat way to look at the clustering algorithm is in this table. In this table, we asked the lawyer to label a small sample of the documents, and then we saw how a clustering algorithm works on this on the labeled data. For example, in the first table, we can see that cluster 1 has two documents that are labeled as A. Cluster 2 has two items labeled as B, and so on. And what we want to achieve, we have two objectives that we want to optimize for. One is that we want as little clusters as possible, because the more clusters, the more work our lawyer needs to do, and thus we pay more. The second one is that we want as little collisions or no collisions as possible. For example, here, cluster 1 has 2 types of labels, which means that one of those labels are going to be mislabeled, and then our whole model is going to suffer from this issue. Next, regarding results. So we applied this method on 35,000 documents, and we were very picky regarding, we didn't want any labeling error. And we got 50% reduction in labels. So 50% less money, and we are all happy. It runs in a matter of minutes or less, depending on your data, but it's not something that you need to run overnight. And you can see here that actually the clusters make sense. So this is only like the first 3 examples out of, I think it was 13. All those clauses actually talk about the same thing. They talk about counterparts or whatever legal mumbo jumbo. Okay, to summarize, we've seen how to do hierarchical clustering in Python using standard SciPy and sklearn. The hyperparameters you need to play with are how do you embed your data, how do you embed the document, how do you convert the document to a vector, how do you measure distance, and what is the cutoff, and where do you measure distance from? How to evaluate. We set 2 objectives that you can optimize for, depending on how sensitive your labeling is. And we achieved 50% reduction without sacrificing any accuracy. Questions?
So I didn't understand the evaluation process. Do you have, where do you get the labels from? From like the lawyers tag all the documents in the cluster?
So it's evaluation in retrospective. We have to ask the lawyer to tag a small sample, so we'll know we're in the right direction. Just to repeat the question, the question was, how do we get the labeled data from? Because if we have the labeled data, then this whole exercise is meaningless. So we ask our lawyer to label a few of the data, like a small sample, 10% or even less. Then we can evaluate our clustering algorithms and choose the best one.
If you have a sample of labels, why not just build a model based on that, take the top features from the model and the output, the different probabilities and cluster based on that? I mean, it would be a lot more optimal.
So the question was, well, if we have labeled data, let's just train classifiers and then derive the clustering algorithm from that. So actually, we might cover just a small sample of all of potential labels that we might have, or all of potential. For example, let's say that we have 10,000 types of classes, and our sample only have 5,000. So it's best just to make sure that in what we can see, we are not making any mistakes, rather than training classifiers in advance. Any other questions? So the question was, how do I know that the clustering is good if I first cluster and then ask the lawyer to label it? So only for evaluation purposes, which is important, I ask the lawyer to classify 10% of the data or even less, and then using that 10% of the data, I adjust my clustering algorithm. Okay, we're out of time.
Thank you, Uri. My name is Omri. I'm a data scientist at Intel. Starting next month, I'm a data scientist at Microsoft. I'll be talking about how to leverage ideas from functional programming, not the entire thing, but just some ideas when we're doing data manipulation in Python and Pandas. So first of all, what is functional programming in a nutshell? So in a nutshell, it's about using functions, obviously. Functions that are pure, they don't have any side effects. It means that every function that we use doesn't change anything outside the function, and it's not dependent on anything outside the function. Declarative versus imperative means that declarative programming means that we focus on what's going on and not how it's implemented. So if you know SQL or SQL, it's a good example of declarative programming. We don't implement the where clause, we just say where, and the language speaks for itself. Thus, it's usually easier to read. And even in non-functional programming languages, there is some support of this notion. So for example, Scala has this kind of API. Java has the stream and function APIs starting from Java 8. In R, everybody started using packages like dplyr, which is more functional than the base R. In .NET C#, there is language integrated querying, and obviously SQL is one example. So let's take a look at 3 chunks of code that actually do the same thing. So one would usually go down this path. So the code is supposed to tell a story other than just solve the problem. And when we do our data pipeline, we usually do something like this. So we take some data set and we send it to a function, get the result, send it to the next function, so on and so forth. Usually it's a lot more messier. It's like hundreds of lines. And the guy that has to read the code after us is miserable. This is another more extreme example where we send every function as an argument to the other. It's actually the same code. And I would argue that this approach, which is it's not very Pythonic, I guess, is easier to read. And there is a problem with the indentation here. But basically, this operator is piping. So we take our data set, we pipe it to the next method with some argument, and then we pipe it to the next one, and so on and so forth. And if we try to read the story of Jack and Jill, then it's just in front of our face. Jack and Jill went up the hill to fetch some water, etc. So we talked about how it's working in other languages, and let's take an example from dplyr. I know people don't like R, but it's a good example. So R had the notion of data frames a lot before Python did, and people used it, and it was fine until dplyr was released. And then people started using dplyr and never looked back, basically. So in dplyr, you use all kinds of verbs, such as select, filter, arrange. People usually know them from SQL. And you create a data flow through piping. Another great feature of dplyr is the ability to seamlessly replace your backend. So the code is not really running in R. You could actually send it to an SQL server or to Spark or to BigQuery, and you could basically change the backend with a change of configuration without having to change the code itself. So as an example, we take a data set, we pipe it to maybe a function that we wrote ourselves, and then to the verbs that dplyr offers us, and we get the final product here. So we're not here to talk about R, so let's look at on one approach, do this in Python. It's just one approach. You could do it in many, many ways. The package is called dfply. It's a Python implementation of dplyr. It's built on top of pandas, so you could use it with pandas interchangeably. And in many cases, it's just a wrapper up on top of pandas. It's a work in progress. It's not completely mature, but again, it's just one option that you could use. So I'm importing dfply, and I'm calling diamonds. Okay, so sorry, not used to Mac. So instead of calling diamonds.head, I'm piping diamonds into head, and I get the head of diamonds. Diamond is a data set of diamonds with different attributes, obviously. To select a column, I pipe diamonds into the select clause, and I could either call x dot name of column, or the index of the column, or a string with the column name, and I get the result. So the syntax is, in my opinion, a little better than what pandas originally supports. To filter out a set of records, I pipe diamonds into mask, where the cut is ideal, the color is E, and the price is lower than 500. Okay, and I could go on using other verbs, such as mutate, which actually creates new columns. I could use functions like lead and lag. I could do different types of joins, and it's basically a different syntax. You could achieve the same thing with pandas, but maybe the syntax here is nicer. Window functions, so I group by, and for every group I calculate the lead and the lag of some variable. And if we compare the syntax of this package with native pandas, then in these two examples, we do the same thing. We group by and we summarize. We look at every group, at some statistic of every group. And you could just see if which interface is better for you. But this is the same idea to use just in pandas. Okay, so key takeaways is that if we even if we're not using this dfly package, we're just taking some ideas from functional programming, and we're doing atomic functions that are pure. We are able to use the code again. We're building a set of tools for ourselves. It's much easier to unit test because we have a function that doesn't interact with outside environments, so it's easier to unit test it. The readability of the code is usually better. In my opinion, you could just start piping your flow and see if at some point there is a problem with scalability, and then drill down and see if you can improve the code under the hood. In dplyr, you could replace the backend, and the good news is that pandas 2 actually do this for us. So starting from pandas 2, we will be able to get better backend support. And because the verbs are quite similar between environments, then if you have to migrate your code from Python to a different environment, then it's usually easier. So that's it. Thanks. Questions?
Are there speed advantages over pandas, or just a readability thing?
Usually it's the same. It might, because it evaluates differently, it might be might be different from pandas. But again, try it and see if it works for you. Then okay. If not, you can always go back to the original pandas.
Is it supports a kind of a pipeline object like we have in pandas sometimes, or like for feature extraction stuff? Like, can I save it as a pipeline in a way?
I'm not sure if it does. I don't think it does. This package, at least. Maybe there are other alternatives that do.
Okay, hey everyone. I really like this short talks format, so thanks for having me. My name is Yair. I'm the head of data science at Windward. We do some kind of maritime AI stuff, trying to get insights from what's happening on the oceans. But you're not going to hear about it today, so if you want to talk to me about it, feel free. We are also hiring. So when I started to think of what I want to present, I thought maybe I should talk about these beautiful Plotly dashboards, or maybe give you some tips of how to profile your code on using Jupyter notebook visualization like SnackViz. But then I thought to myself, why give you something practical when I can talk on whatever I would like to? So I'm going to talk about something totally not technical, of how to become an impactful data scientist. Short survey: how many of you found themselves doing work that they thought was insignificant to their business? Like, what am I doing? That's very few people. Good for you. On the other hand, how many people found themselves doing, like, trying to solve a problem that was really significant for their business? Like, cool. So I want to push forward towards the second side of the spectrum. Let's talk a little bit about motivation, why impactful is good. So the obvious thing is, if you are influential, you're going to get paid, and you're going to be valued. Two great things, but I think the most important thing is that we like to do stuff that matters. Okay, we are sitting 8-9 hours in front of a computer. We wanted to count, right? So this is, for me, the most the main motivation. So while I'm talking here, you all know these Venn diagrams of data scientist skills and stuff. So what I'm suggesting is to maybe even demand more of ourselves in terms of business understanding. It is related to the domain expertise area, but it's not really the same thing. But that's like the direction of this talk. A few practical things that you can do to be more impactful. So first, you must understand the context and business needs. In the military, it's always advisable to know like 2 levels above you, right? If you are a platoon commander, you need to know what's happening in the company and the battalion level. So if we take the analogy to the tech world, you need to understand what's not happening not only in your team, but entire R&D group or the closest 60 people you're working with. You need to be brave enough to ask questions, both, I don't know, your team leader, product guys, not being like the annoying kind of data scientist, but really trying to understand why is this important? Why are we doing this and not that? And try to really understand the motivation. Your work will be much more guided if you do so. In order to do it, you need to get out of your bubble. Most of us sit in our laptops in our corner. You really need to start talking with other people. In startups, it's really easy. You go and you talk to the product guys, the sales guys, maybe even clients. But you can do it also in larger organizations. Talk to other groups. Try to understand what sells. Okay, it's really important to get the general idea, and you can also make some useful allies along the way. We're not playing the Game of Thrones here, but these guys can help you push forward your initiatives. I will get back to it in a few minutes. One thing that is often overlooked is planning the project, the data science solution. I explicitly wrote a data science solution here because we're not building a model. We're not trying to win a Kaggle competition. We're trying to answer a business need. And sometimes this first critical stage is often overlooked. I'm feeling like a rock star. So basically, you need to understand what you're trying to solve. You need to plot a mock, like a simple graph, how the solution would look like, even on a piece of paper. You need to understand what the metric you need to optimize, not just run and build features. Okay. In the book of Thinking with Data Science, they have this acronym of CONVO. You need to understand the context, the need, the vision, and the outcome of how the solution would look like. And it's recommended to start thinking in this way. It's very important to understand trade-offs. What is more important, precision or recall? It's just one kind of trade-off you can start. And another thing that I urge you to do is not to be afraid to start with simple solutions, okay? Don't say like, oh, me, decision tree? I don't do decision tree. It's like a stupid model, but it's more interpretable. It's easy to debug a decision tree at the beginning, right? Maybe don't even start with machine learning. Just try a simple heuristic. Gather data. Try to understand if you are solving the problem. A very advisable reading is Rules of ML of Martin Zinkovich from Google. The best 25 pages you can read on building machine learning solutions. Very recommended. One more thing I'd like to suggest to you to start a side project. We all know Google 20%, and not every company is Google. So, but my experience is that basically innovation doesn't come from yearly plans or quarterly product plans. People, hear great ideas and they want to implement them. They have like insights, and you need to push forward your good ideas. Don't tell your boss I need a day a week. Some managers can be afraid of it, but try and say, I have this idea, I want a few hours a week, like an hours every day to work on it. Usually you will get the support you need. You need 4 things that will make your efforts more focused. So first, it needs to be interesting because you are the only one that cares about this project. So if you don't like it, no one else will. The second thing, it needs to be doable. Don't start building massive infrastructure. It has to be something that you can do with existing tools. It usually happens that a new tool is added and then new capabilities and new ideas come along with it. So it needs to be doable. It needs to be impactful. Don't try to just to improve the tiny bit of existing solution because no one would care. And it also needs to provide value pretty early on. No one will wait a year to see your results. And it is very important to understand that you're not building a product here. You're building a POC. You're building something that will create enough traction and curiosity within the organization. And people say, "Wow, this is cool. Let's put some real effort into it and put it into our product." In Winwood, we had a couple of successes of people doing their side projects and pushing them, and they became really meaningful parts of the product. That's about side project. You also need to publish your work. We usually stop once we solve the analytical problem. You usually stop caring, or it's less interesting for us. but it's really important to get feedback and engagement of other people in the organization. You need to invest in tutorials, documentation, APIs, especially for non-technical people. And it's really important to talk to the allies you made on section number 2 and ask for their opinion. If no one uses your internal tool, for example, you need to understand why. It's very important to get feedback on early stages of your work. So do like off-product revealment of parts of your solution. About software engineering things, how many of you learned software engineering in university or something? Okay, so more than half didn't. I really advise you to get like paradigms. So like get a few ideas that will make your work much more efficient. Each one of them is like an hours of lecturing, but code reuse was mentioned here. We all know these spaghetti Jupyter notebooks that you need to start copy pasting. And if you're using the code for more than one notebook, you need to package it in a source control environment. It will make it easier for you to test your code and share it between other data scientists. So try to understand how how you can be a better software engineer. Profiling your code, if you have like an algorithm that runs for 20 minutes and you're just waiting or browsing, I don't know, Facebook, waiting for it to finish, try to make things a little bit faster. This is, by the way, a very interesting link of how to do it for data scientists. Automation is also a great way to save time, although this XKCD comic says otherwise. Push enabling tools. You come out of this meetup, you have many ideas, you saw some great stuff, push it to try to promote it within your organization. Create dashboards for non-technical people to view the data and come up with new ideas. It is really a worthwhile effort. And the last thing I would like to briefly talk about is retrospective, which is done in also software engineering methodologies like Scrum and Agile. I suggest, I did it myself, take a last year of your project in your workplace, try to rate them as low, medium, and high influence, and try to understand what is what. So basically, time is up.
Questions?
Yeah, just even if you don't implement all of them, just take 1 or 2 and you'll be better off. Thanks.
Hey. Hi, everybody. Thanks for being here. My name is Omri Allouche. I'm a senior data scientist at Gong.io. I also teach data science at Bar-Ilan University's Faculty of Engineering, and today I want to show you how to create beautiful interactive reports automatically using HTML. So the slide contains shameless promotion because we're hiring, but I would use Gong as a case for what I actually want to present. Gong automatically records, transcribes, and analyzes B2B sales calls. We try to help salespeople be better at selling with giving actionable insights and recommendations as to what they can do. Okay, yeah. So let's just jump right into things. Let's say we're asked to create a report about the sales results of our different clients. We have many clients, and for each we want to show a table with the performance of each of their sales reps, the contact information of this sales rep. We also want to show the revenues of the company by month and by industry. The problem is that we have dozens of clients and we have to do that repeatedly, periodically. That's a lot of work. Okay? So even if we get a basic file with all of our information, okay, try to think what would be the best way to actually create a report like that. I would argue that using a PowerPoint is just not suitable for the task because we'd have to manually create the presentation, the report for each company. Doing a Jupyter notebook involves the code inside. That's not really something that you can send to people. They have to have a server. It's not really very useful. So what I suggest is to use HTML. I haven't seen many people do that. I think it's highly effective in sharing reports. Basically, HTML is a text format that includes tags that browsers can render and display. We can create HTML reports since they are text files automatically. It's very simple. We can include interactivity using JavaScript, very basic JavaScript. We can style them beautifully. They're very easy to share. You just attach the file or put it online, even as I do here with GitHub pages for free. They open on all devices, including on mobile phones. Nobody has to install anything. It just works. So let's see what we try to create here and give a better insight as to how it works. OK, so this is pretty ugly. I didn't have time for the beautiful report that we created for one company. Okay, you can see that we have a table showing the different salespeople of this company. We can also sort according to the different columns. We can search and filter according to different results, and we can paginate, so results load basically easier. We can get more information about each of the salespeople. Okay, so for each one, we have the phone and email if we want that, and the results of the salesperson. We save space, but we also include the reports for the performance by month or by industry, and all of that is created automatically. Okay, now I'm going to talk really quickly because there's a lot to fill in those just 10 minutes that I have, but basically this is created from a Jupyter notebook that I'm going to share. If you run the code, it will generate the report. I'm just going to quickly touch on the main aspects of things. Great. You don't have to do this step, but you do need to install Pandas and Jinja 2. Jinja 2 is a templating engine for Python. Basically, it gets either a string or a file that contains placeholders instead of the variables instead of the values that we want to use. And we compile this template and render it with the actual values. The syntax is very similar to Python. We'll see it soon. It allows loops and conditionals, works very well with Pandas data frames, and can be extended. So let's see a basic example. These are the top 3 salespeople in the world. And we just passed those as a list. Okay? We define the template here. 8.3 means a header. We just reference one of those. We load the template from a string. We render it with our data. And then we display it as the HTML, and we actually get the results. Now, what I got here is an HTML, is a string of HTML that the Jupyter notebook can render on screen. But that's something that I can save to a file, send to someone, and you'll be able to see the report. OK. To style our report, we can use Twitter Bootstrap. It's a framework developed by Twitter that contains many different elements of HTML. It's very easy to style elements using CSS. It gives us the accordion that I've shown here to the right. It gives us the division into 2 columns and many other things like this alert, for example, that I can dismiss if I want. Okay. The tables that I've shown and made it interactive, all we have to do is just get a Pandas data frame. We can use Pandas to HTML function to save it as an HTML table. Better use a function that I created that's given here and allows more control in the HTML over the table. If we add this snippet of code below, the table automatically becomes interactive. We can sort it. We can filter it. We can paginate through the pages. And if we want to create our actual report, and this is the code that generates that, we just import the relevant packages. We load the data and focus on just the one company that we want. We group our sales information by the salesperson, the industry, and the month with simple group by function of Pandas. So we create different data frames, okay? Here by industry and here by month. We create the bar chart just by using the Pandas plotting function, and we save it using matplotlib's savefig function to a file. Then we can link in HTML to the file itself using the image tag and the source with the actual file name that we saved. That's one option, and you can see that we render the file. An alternative is to use a base64 representation of the image. That means that we can inline the HTML as a text string, save the image itself. We don't have to have a different file. This is a function that does that. Okay, you can see how the beginning of the base64 string looks like. It's not very important, but this will be inside the HTML if we do this thing. And then we pass our data into the template. So we can pass the data frames that we created earlier. We can pass the string representations of the images or the image file name, and we can even pass functions and use them inside the template. The syntax of Jinja 2 is very similar to Python. You can see that we have a for loop here. We go over the sales people using iteros of pandas. We can use conditionals for if. We can apply many other things basically just to show the information. Here we load the template from a file. So I have a file with all of the things that are included. We render it with the data. And we save it to file as just a simple text file here. And eventually, we get the report.
So, hey everybody. My name is Erez. I work at Salesforce. Part of as part of our data science team here in the Tel Aviv office. So in this short lecture, I'm going to talk about the first part will be why is it important to explain machine learning models and not just provide prediction. And the second part, I will talk about how we dealt with this problem in some of our projects. So imagine for a moment that your salary, your bonus, your compensation depends totally on a black box that gives you an number. How good would you feel about it? So for us, for many of our customers, this is not very far away from the truth. So in one of our projects, we have to provide the likelihood for a deal to close. Salespeople, our customers, are compensated based on the amount of deal they are closing. So we want them to use this feature to allow them to choose which deals they should invest their time on. And if they will invest their time on the wrong deals, they might not get the bonus, they might get lower salary. So obviously they will be pissed. So one of the things that we encounter is that they don't feel, obviously they don't feel confident enough just by a system that gives them an upper. Now I have to say that some customers are okay with that. Some customers are okay with a system that just gives them a magic number. They don't care how it works. This lecture is not for them, but most customers are not like that. So one of the ways we found out that if we can provide some insights toward how the system took the decision, what was the important factors in taking this decision, it will make our customers trust the system more. It will ease the integration of the system in the organization. There is also not necessarily a positive side effect that they will want more control. So when you are telling the customer, hey, I took this decision based on the fact that I see the opportunity or the deal is from certain geographical area, many times the customer will come to you and say, hey, don't use that field. I know better, it's not relevant. So you also need to take this into account. So by now, I hope I gave you a clear reason why we have a great motivation that provides a good explanation to our prediction, and why explanation is sometimes more important than the prediction itself. So by the time we started to work on this project specifically, we already had a working model that gave us the prediction, that gave us the likelihood. That model happened to be a random forest that we trained. And we did what we usually do when we encounter a new project. We start out with the simplest possible solution we can think of, and we decided that we'll make it as complex as we need it to be. So in this case, what we decided is the most natural approach. We said, hey, a random forest is composed of many trees. A tree is a relatively easy model to extract the decision from. We just look at the decision path. We will look at how much each feature contributed to the information gained there, or whatever metrics we are using. And based on that, we will basically create a message that say, hey, this feature with a more human readable name, with this value appear in this deal, and based on that, we think it's more likely or less likely to close. So we did this, and we tried out on small number of customers in a pilot, obviously. It worked, but it didn't work quite as well as we can. We can do better. So the things we learned from this is that what makes sense for us as a data scientist does not really make sense to customers. One of the things, I can give you an example, is let's say that certain opportunity or deal does not have a geographical region. So for me, it makes perfect sense as a feature. But when you display something like this to a customer and say, hey, this deal is from no geographical region, then I think it's less likely to close. They don't like it. It doesn't make sense to them. They don't understand that there might be an underlying process that because of it, it doesn't have that feature. Another problem we had is we had many highly correlated features. So sometimes we had to translate each one of those features to a key factor or to explanation, and that could cause some time for sort of completing or duplicated messages. So obviously we realized, at the end of the day, we realized that our message was not clear enough, that it was not simple enough for them, and it didn't get the job done. So basically, we realized we can't use just raw feature as the explanation. We need to do something better. But we have a problem. And the problem is that in order to provide a coherent message, in order to provide a good explanation, we need a simple model, something which we have high degree of control, that it's easy to translate. But on the other hand, if we want to keep high accuracy, and it is important for our customers, we have to go to the direction of more complex model and use many features. So we are having sort of tug of war, which is even worse because we like to use discriminative model, like trees, which are less clear to explain. So we decided to split. So let's use two separate models. One model will be used for the prediction, and another model will be used for the explanation. Now, there are some advantages to this decision. One of them is that it allows us to freely change the prediction model and use a number of different prediction models with high degree with different degree of precision without needing to change the underlying explanation behind it. So this is a great advantage to us. And it also allows us to get explainability and accuracy without having a trade-off. Now, there is an issue here that we might get sort of conflicting information between our models, because we're using two separate ones. So this time we started out and we went very differently. We talked to customers, we talked to internal sales rep, we talked to product manager, and we created a very big list of possible explanations towards why a deal might have high likelihood or low likelihood to close. We then look at our feature. We only took explanation or reason that we can actually justify. We throw away others. We decided to use two models. We used random forest because it's very similar to the prediction models. We also use a linear regression because it's a relatively simple model. And the simpler the model, if it gets the job done, it's better. Now, instead of training those models to actually give us the prediction, we train them to minimize the error against the predictor. This way, we're actually making the model correlate with the predictor. Another thing I haven't mentioned is that we actually hand-build the feature to justify the different reasons we had. And we actually had to build them differently for random forest and linear regression. And eventually we picked the linear regression and stopped investing time where we don't need to. So that's it. Just about the tools we are using, just in time. Yeah. So we are using a Jupyter notebook. Obviously with sklearn and pandas, we can use Spark if we want to. What you're seeing here is actually a graph of how the likelihood of opportunity to close change across time, which is caused by changes to this opportunity. We are actually using widgets inside the Jupyter notebook when we actually can search and browse the different opportunity so we can debug them and understand problems or other things. So here's another widget we are using. Again, I'm not showing you the notebook, but this is actually from a notebook, which we actually can put on opportunity, look at the different factors we have, how much they contributed, etc., etc. So that's it. Thank you. Any questions?
Good evening. My name's Liron Heyman. I'm a data scientist at Intuit. Intuit is a multinational fintech company working in the personal finance space. And we are also hiring and growing an AI and ML center in Israel, if you want to talk about it during the break. Tonight I'll be talking about balancing classes in Python. And I have two main things on the agenda. The first thing is just explaining the motivation behind why we sometimes will balance classes. And secondly, showing or explaining a useful Python library, which is a bit less known, which can be useful in this space. And if you fall asleep in the next 10 minutes, you can just go to this link, and there's a lot of really good code and good explanations there for what I'm going to talk about. So let's take a motivating example outside of the finance space, just a simple screen for cancer. We know that, typically speaking, most patients will be healthy, so a lot of models can just be, you're healthy, you don't have cancer, you're healthy, you're healthy. But that's a bit of a useless model because we're missing the interesting cases of patients who have cancer. Shir, don't worry, I'm not going to talk about what you're talking about. There's a fallacy of accuracy with imbalanced classes where the minor class is interesting, but it's not being picked up by the model. And we want the model to hear the voice, what I like to say, with the minor class. And that's why balancing classes, meaning making the minor class equal to the major class in size, becomes really useful. There are two minor points I will raise here but not discuss. The effect of balancing classes depends on the classification model you end up using. SVM, decision tree, logistic regression, etc. There's no time to talk about that tonight. And you can extend what I will talk about beyond binary classification cases. Just for simplicity, I will stick with binary classification. So let's map out the options when you balance classes. On the left-hand side of this tree, you have basic sampling strategies, which means let's stick to the data that we have in the data set and not create new fake data, but either oversample the minority class by just like Control-C, Control-V, basically, of random data in the minority class, or undersample the majority class, just removing cases from the majority class. So what I have in the bottom left corner is random sampling strategies, which a lot of us would intuitively suggest, which is what I just described, which I won't discuss because it's a bit less interesting and it doesn't work so well when you train a model. So I will talk about the green text over here. The first thing is atomic links, which is a strategic way to decide which data points to remove when you want to undersample the majority class. So what is atomic link? Atomic links are defined by when a data point's nearest neighbor belongs to the other class or another class. And the idea with atomic links is to remove, if a point in the minority class, if its neighbor belongs to the majority class, we basically want to remove that point from the data set. Why do we do this? Again, like I said before, we want to hear the voice of the interesting cases in the minority class. So here we've got these blue points in the minority class. The black points belong to the majority class, but before we train a model, we remove these black points from the data set. Again, a lot of you will ask, are we cheating? Our goal isn't to be loyal to the data. Our goal is to train a model that works, and that's why this is okay. Sorry, that's why this is okay. So atomic links are a really useful pre-processing step in the next steps that I will talk about now. It's not used isolated, generally speaking. On the right-hand side of this tree, you have a very interesting strategies over here, which is what I call synthetic data generation, which means that the data that we end up using when we train the model doesn't actually exist in real life. We might be using data points which we've created from thin air, basically. But it works to train a model, so it's okay. So here we have, and this is, the Python library is called imbalanced learn. You just pip install it. This is where you have smote and @assign, and they're really simple to implement. I don't have the code snippets here, but it's a single line of code to import it and 2 lines to run it. Smote stands for synthetic minority oversampling technique, and @assign stands for adaptive synthetic. I'll have time tonight to talk about smote and its variations. So smote, the idea is as follows. When we want to oversample a point from the minority class, what we do is, instead of this Control-C, Control-V that I mentioned before, just creating duplicating a new point, what we do is, we find a point in the minority class, we find its nearest neighbors. We say k nearest neighbors. K is usually 5. You can play with that parameter. It's k nearest neighbors belonging to the minority class. So we see these 5 blue points over here. We randomly pick one of them. And then instead of just Control-C, Control-V, like I say, one of those points, we choose a random point on the vector which connects the 2 points and create that new data point over there. So that will enter the model, that big blue dot over there, but it doesn't actually exist in real life. But it's good to train a model. So here we have an example of this in action. In the top, we have the original data set. And over here, we have and the blue class is the minor class. Over here, we have it being implemented. And as you can see, all these blue points over here in that what's usually a white space in the original data set. So we've created these like synthetic data points, which don't really exist, but it's good for training a model. There are 2 disadvantages to this vanilla smote, the plain application of smote. The first disadvantage is that we are resampling every point in the minority class equally, which isn't necessarily what we want to do, and I'll explain why. Basically, some points in the minority class interest us more than others. Points closer to the decision boundary are much more important for the model to hear its voice. So we might want to be resampling those points more than the points very safely inside the region of the minority class. The second disadvantage is that we are always restricted to the region of the minority class, meaning all these new points that are created stay inside the minority class. And there's no real reason for that restriction, meaning we could easily have new points outside of this region, and it could actually help train a model better. So there are 2 variations to smote, both also in this imbalanced learn Python library, which solve each of these disadvantages. And I'll start with borderline 2, and it'll become clear in 2 minutes why I started with 2 and not 1. So 2 comes and solves this issue of having all the new data points being restricted to the original region of the data set. And it does it by saying that when we choose these k nearest neighbors over here, don't just take the k nearest neighbors from the minority class, but you can even take the nearest neighbors from the majority class as well. And by doing that, you end up getting new points outside of the region of the minority class. Now, in order not to become too extreme and just have this random data like sparsely thrown out of the region of the minority class, we multiply this by this small random number close to 0.5, which basically allows a point to still be closer to the minority class, but not restricted to the original region. So that's borderline 2, which solves that disadvantage of having the new points restricted to the region of the minority class. Borderline 1 solves this problem I mentioned before, that all points are resampled equally. And it does it in the following way. It says, let's divide all the points of the minority class into 3 cases. The first case is noise. And this is where all of its neighbors belong to the majority class. And the decision that the guys who developed Borderline 1 came up with is, these are just outliers, get rid of these points. You can argue about that claim, but that's what the algorithm does. Then you have the safe set, where the majority of the neighbors belong to the minority class. Those points we don't really want to oversample because they're already so safely embedded inside the minority class, so there's no interest in resampling them. What is interesting to us, please work, is the danger set, where the majority, but not all of the neighbors, belong to the majority class, and those points we really want to resample. So we will do smoke, but only on those points. And this is the results of Borderline 1. As you can see, we've resampled a lot very close to the decision boundary. We haven't resampled at all away from the decision boundary. That's Borderline 1. Add sign is basically the same as Borderline 1. It just has a slightly different algorithm, which I don't have time for. So this is the results of add sign. It's having the same solution, where the new data points from the minority class are outside the original region of the minority class. And also what add sign does is it says, let's resample proportional to the number of neighbors that exist in the majority class. The more neighbors that a data point has in the majority class, the more we want to resample that point. In summary, the recipe for success: use atomic links as a pre-processing step to remove majority class data points we don't want, and don't use vanilla smoke for those two disadvantages that are raised. And again, if you fell asleep, but it doesn't look like any of you did, see that link. Thanks. And so I'll reword the question as a note, that perhaps removal of points from using atomic links is not a good idea, because you want those data points from a majority class, and you just want to be resampling minority class points close to that. I fully agree. I recommend, do like every answer here, do both and compare your results. You're right, sometimes it's not the right solution. I would say if you had to pick one thing, just remove them as a quick solution.
Did you get to use this in your work?
I did get to use this in my work. We were predicting overdraft incidents of users who spending their money in the US. In the US, you get a $34 fee every time you overdraft your account, which is insane. And it's a rare event, as you can see. It's not like 0.04%. Balancing also works if you've got like a 14% class or 15% class. What's nice these days with computing power is you can always just try something and compare results.
Can you go back a few slides before?
This one.
More. I think when you said to connect the minority, to create a synthetic minority class, connecting it on a majority class. I don't fully understand the semantic behind it and how you ensure, this.
Yes.
When you add this blue point inside the majority class, how you ensure that you don't switch the semantic of your synthetic data? How you ensure that you keep being a minority?
Every point has a label. So you still, the label for that point will be minority.
You create it artificially.
Yeah.
But how you show you're not tricking your net? How you show you...
So like I said, you are tricking your model, but the goal here is to train a model that will end up predicting real data well. So I could train a model on numbers that I invent in my head, and if it has good results, I will use it. This is a philosophical question. I think it has results, so it's justifiable. I think we're going to the break time, so thank you.